Okay, let's go ahead and continue with our example by taking a look at how we can now start visualizing the form that we just created. So you might remember that we have set the building form to two parameters based on the either highest or lowest combined value, the test case that gave us the highest or lowest combined evaluation value. And we set that up. And now we're going to continue with basically panelizing those wall surfaces and adjusting their appearance. So to panelize the wall surfaces, we're actually going to use some fairly familiar functions. We're going to use a custom node to basically select the wall surfaces. I need to select those wall surfaces because what I want to do is be sure to grab the latest wall surfaces as opposed to some manually selected ones. I want to grab them programmatically after the form has been reshaped. Then I'm going to panelize by surface, UV. Now, that's a function that's actually fairly familiar. We used that function and created that function originally as part of the assignment where we were applying the photographic data to the panels. We should, though, however, download the latest version from the shared library. The original function was set up in such a way that it handled a single surface. I've kind of enhanced the function so now it can handle a list of surfaces better. So make sure you download the latest version to go through and work with that. And let's just kind of look at how that step looks as we get started. So we've run and created our basic building form. That's the output over here. This is the updated mass. That's looking good. I'm going to basically take that updated element in as the input for select the wall surfaces. This node basically just sorts a building form, kind of computes the normals to all the different surfaces and says that if your normal is -1, okay, that means you're pointing straight to the ground. I'll consider you a ground surface. If it's pointing at 1, or if the value is 1, or the z-value of the normal, I should say, is 1 or close to 1, I consider you to be a roof or a flat roof. I allow a little bit of leeway in there because things aren't always perfectly flat. So I'll say if your value is over like 0.95 or something like that. If neither of those cases is true, I'll consider you a wall surface. So this will just sort things out into a list. And I'm going to take those wall surfaces down to our panelize node. Now for this node, watch out for to make sure that you have the latest version of the node. If you have the latest version of the node, it'll say surface to panelize if you're using mine, as opposed to just SRF. Also, if you open the node, check for this. The input should be a list of surfaces as opposed to just a single surface. It makes a difference in terms of how things will get processed. So if it's expecting a list, it'll handle things and kind of take care of all the different items on that list. And since we're going to have more than one surface, we want to basically have it do this to all the items on the list. So let's go back on over and give this a try and see how it works. So I'm going to panelize those surfaces. Let's go through and give this a run. Oh, you also need to go through and specify a family type. In this case, I'm using the rectangular panel with an opening. Again, I'd stick with a fairly simple family type like that one as a starting point because, that's known to work pretty well and can handle a lot of interesting deformations. So I'd probably start with that one. That one's pretty rock solid in terms of being able to apply it. Okay, but you will need to go through and select a family type as one of the input parameters. You might notice that the first version of the tower has the panels associated with it right now. It's evaluating the other versions. Finally, those panels will be updated with a final version of the tower. Okay, when this all completes. But it's a little disconcerting at first. Often you'll get sort of some power panels that appear to be floating in space because it's just based on the initial building form. It runs one run through and does that before it starts implementing all the logic. Okay, so it finally caught up with itself, and you can see that now we have a list of these different panels. We actually have 3 different lists of panels. 1, 2, 3. We have panels on the 3 different surfaces, the 3 different wall surfaces. So that's what's going on there. What I want to do now is actually think about going through and kind of taking those panel surfaces and computing all the different dot products and giving me the scaled values here. So let's go ahead and bring that on down. We're going to use those values to actually do some colorization as well as kind of changing the panel opening. So just to kind of follow the logic through, we're going to use our panels compute sun directness, again, with this important caveat. Okay, the caveat is that sun directness kind of takes into account the geometry, okay, facing towards the sun. Okay, it doesn't take into account any sort of shading effect though. So using this is kind of a relatively quick way of evaluating directness. Okay, we do it if you want to kind of get quick results because computing geometry is very quick. Okay, but it doesn't take into account self-shading. If we wanted to account for the self-shading, we need to do a solar radiation analysis on each of the different panels. That could then say there are some shading surfaces as well as the analysis surfaces and get more accurate values for how much sun's actually going to hit there. But for quickness, I'm just going to go ahead and illustrate this by doing the sun directness, again, based on the geometry. Once we have those, we're going to colorize the panels. We're going to remap the range, okay, so that we can have a list of values that we can use to set some parameters. And for that opening, or the panel with the opening, we'll kind of set the size of the frame around the opening, kind of based on those, okay, as we did in one of the prior examples. So let's go ahead and take those down. I'm going to take my list of the different wall panels. Okay, going to compute the scaled directness values. Going to bring them over here. Actually, I'm goofing a little bit right here. What I need to actually do is get the panel surfaces, not the panel elements, and bring them on down there. Okay, I'll do the scaled directness values. And then those scaling values, I need to fix the spelling on that, and I will. Need to basically get the panel elements themselves. That's these. So I'm going to scale based on the surfaces. On compute burst, it's based on the surfaces, but I'm going to colorize the panels. Okay, so that should set up the actual colorization of the panels. In terms of actually thinking about how we can use those values to do the color or the rescaling of the openings too, what I'm going to do is again take those directness values, those scale directness values, and just remap them again. Anywhere between 0.5 and 0.4, that's the range of values that is valid for kind of thinking about this specific opening. If I choose one of those panels, you can sort of see it has this frame opening width, and we can kind of set the percentage that we want to allow to be open in each direction. Okay, anywhere from very, very open to very, very closed. And then I can set the parameter by name, setting the parameter value names to those values. Okay, let's give this a try and see how things work. Okay, looks like it's computed the values. It's adjusting the opening sizes right now. Actually, it did it on the initial list of panels. The tower is actually now doing its evaluation. Okay, it's kind of evaluating all the different potential tower shapes. It's going to figure out the final shape here. And then it'll adjust all the final values there. Super. Okay, so we have all these directness values that came out. We have all these dot products, and we have all these solar directness values that came out. They went over to the panel colorize, and now we have a big old list of the different colors that'll be applied. I actually have also now a list of all these different values. Okay, notice they're sort of sorted out on a kind of wall by wall basis, on a wall surface by wall surface basis, and that's kind of okay. So those three different walls, same things with the color values. Three different wall surfaces. So we're looking okay. And now as we pull those forward, those all come forward and we set the parameter values by name. So now we get, okay, all the listed different panels over here. Let's take a look at it back over in Revit. Again, all visibility graphics, turn off the masses just so I can sort of see the panelization a little bit better. You sort of see the directness. This is sun directness. So there's south, depending on what time of day it's actually set to right now. You can sort of imagine the sun being over there. Back over here, the back side of the panel, that's really more towards the north. It's more blue, it's more open. It's actually looking pretty good right now. So that is, panelized in a fairly gross way. That's just kind of giving you kind of an overall sense of it. If you really want to get fine and kind of make it look more like a real tower, we could think about, just changing some of the input parameters back over here. Didn't really kind of talk about them very much, but way back over on the front part of the graph, we have the number of panels we want to place in each of the different directions. So if you wanted to kind of have something that was a little bit more fine or kind of change to a different panel opening, you can do something like that. Let me do this to, 10 by 10. Again, that's about as high as I want to go. That's going to be 100 on each different face. Let's give that a run as this finishes out. Okay, so again, after it works, then you can go ahead and go hog wild in terms of getting something that looks a little bit more fine. But before that, go ahead and test it with a relatively small number. Okay, I'll just let that go ahead and finish running. Okay, so as that's finishing up, Lem's just going to give you a preview of where we're going next in our next module. In this module, we've been thinking about this whole notion of really mostly just computing these different evaluation metrics, and we kind of came up with a very simplistic way of thinking about how to combine those metrics together. We combined them together using just sort of a kind of a weighted function that added all the different values together. And again, depending on what you're trying to achieve, that's probably a pretty simplistic way of trying to figure out what we consider to be the best alternative. Where we're going to go in the next module is to start thinking about that a little more sophisticatedly. We're going to think about there really being kind of, as we're comparing these different objective functions, different cases that could equally be considered attractive, just, depending on how we look at it. So we're going to think about how we can actually kind of plot these things more than as a single value, but kind of think about plotting them out in kind of n-dimensional space. So we can start thinking about the plateau and which ones are in sort of better locations versus worse locations. Okay, so we can start isolating the ones that are on this frontier. We call it the Pareto frontier, where things are sort of equally attractive, and either you're on that frontier of equally attractive things, or you are just unrealistic or just unattractive as a potential alternative. So that's where we're going next. We're going to really start thinking about how we can do this optimization in a more sophisticated way than just iterating through all the alternatives and kind of coming up with this simple evaluation. We're going to get into sort of true optimization. Okay, so that's what's coming up next. Okay, as this continues to compute, it looks like it's regenerating all my panels now. It's going to go from 75 panels to 300 panels. Let's see if it's going to do it. It's still sort of working. But again, I think this is illustrating how it is just very slow, kind of when you're generating those Revit elements. So that's a little more fine looking. Looks like I might have an outlier there. Either that or that just happens to be just perfect. I think that value may be a little bit off in terms of the normal there. But that's actually looking pretty good. Okay, so that's where we'll continue. For now, you're going to go ahead and build your own example of how to take the building form that you created and implement some evaluation functions on it.